It is a great pleasure for me to introduce our first speaker of this spring semester on lectures on algebraic graph theory, Professor Tao Feng from Beijing Jiao Tong University. Actually, at the end of November last year, I have participated at the conference. I'm not sure what is the title. It is something like Algebra, Combinatorics, and Finite Geometry, where Professor Tao Feng gave an excellent talk on difference families. And after his talk, it was something like a discussion about what exactly are applications of difference families in algebraic graph theory, in coordinate theory. So that is why I decided to introduce him to give two lectures about this subject, I mean, this sets of difference families, and explain us what actually are applications for this. And yeah, so Professor, let me introduce just a little bit him. So Professor Tao Feng received his PhD from Beijing Jiao Tong University, and now he's professor at the same university, right?
Yeah. Yes.
Yeah. Yeah. Okay.
Yeah.
The floor is yours. Okay.
Yeah. Yeah. Thank you. Thank you for introducing me. Yeah, my talk is on difference families, and actually, I will only speak a few applications, not too much in this lecture this time. First, let us see what's the definition of difference family. Let G be a group. For convenience, we use plus as its operation, but the group not necessarily abelian. Let H be a subgroup of G. A difference family is a family of K subsets of G. This family, we use flower F to denote it, such that the multiset dot flower F consists of differences coming from all possible pairs of distinct elements of this K subsets. If this multiset covers each element of G minus H exactly lambda times, then the flower F is called a difference family. And generally, convenience, we call each K subset a base block. I will illustrate what's the meaning of base later. To understand the concept clearly, we can count in a difference family, are there how many base blocks? According to the definition, all of the elements in G minus H appears exactly lambda times. So when we count the total number of differences, the total number is lambda times the size of G minus the size of H. This is the total number. And each base block or each K subset can contribute K times K minus 1 differences. So lambda times the size of G minus size of H over the number K times K minus 1 is the number of base blocks in a difference family. Such a difference family is denoted by GHK lambda df. So because this number should be an integer, so we have a necessary condition for the existence of difference families is like this one. When the subgroup H is trivial, generally we omit this notation from the GHK lambda we just written as GK lambda df. 1G is a cyclic group, and H means it contains a cyclic subgroup of order H. Then the notation can be written as V HK lambda. And here is a capital C, CDF. So when we write CDF, it means a cyclic difference family. Here is an example. Now we want to construct a cyclic difference family over the cyclic group of order 7. And it only contains one base block, 0, 1, 3. We can see the pair 0, 1 contributes difference 1 or minus 1. The pair 0, 3 contributes the pair 3 or minus 3. And the pair 1, 3 contributes the difference 2 or minus 2. So all the possible elements, 1, 2, 3, 4, 5, 6, appears as a difference exactly once. So this is a 7, 3, 1 cyclic difference family. It consists only one base block. Next, I will illustrate why people are interested in difference family, because it can produce two designs. Let X be a V set and flower B be a collection of K subsets of X. Each K subset called a block. A pair X flower B is called a VK lambda design if every pair of distinct elements of X is contained in exactly lambda blocks of B. When the block size is 3 and the index lambda is 1, we often call lambda is index. A V31 design is called a Steiner triple system and written as STSV. An typical example is the famous Fano plane, or we call it Steiner triple system of order 7. It is constructed on the cyclic group of order 7. Of course, we can construct a cyclic Steiner triple system of order 7 in any set consists of 7 elements, but here we hope this example can have an additional algebraic structure. Here we list all the blocks. We can see it contains 7 blocks. We can check 0, 1. This pair appears in the first block, and 0, 2 in the last block, and 0, 3 in the first one, 0, 4, 0, 5, 0, 6. And anyway, one can check all the pair occurs in exactly once in one block. And actually, because this example, I believe you can see it admits the cyclic group of order 7 as its automorphism group. Because 0, 1, 3, the first block plus 1 is 1, 2, 4, the second block plus 1, 2, 3, 5. So it contains the cyclic group as its automorphism. If a design admits a cyclic group as its automorphism, and this cyclic group consists of a cycle of length V. V is the number of the set of the points. Then the design is called cyclic. But when we construct a design, we can construct a cyclic design. But if a cyclic design does not exist, it doesn't mean the design does not exist. I mean, the cyclic just one approach to construct a design. Okay. All the blocks of a cyclic design can be partitioned into orbits under the cyclic group CV. Take our above example, we can see all the 3 blocks can be partitioned into one orbit under the action of CV. And we can take a representative from this orbit. For example, we can just take the red one, 0, 1, 3, and we call this block is a base block. And we know that 0, 1, 3 form a cyclic difference family. That's why in the definition of cyclic difference family, we call its elements is base block. But when we talk about design, we call its elements is block. Okay, that means base block can generate to produce blocks. So the relation between design, and the cyclic design is like this. If there is a VK lambda cyclic difference family, then we can develop all of its blocks to form a cyclic design. But the converse is usually not true, because using the above approach, all the design's block orbits are of full orbits. Full orbits means the block orbit is of length v, and of course, for when we construct a design, maybe its block orbit is short. So if the cyclic design must contain short orbit, then we cannot construct it by using a VK lambda cyclic difference family. But if a cyclic design contains short orbit, we can use another type of cyclic difference family. For example, here we can use VKK lambda cyclic difference family. We record the definition. Here, the first K means K, the cyclic group of order V contains a subgroup of order K, or that means K divides V. Okay. Here is an example to illustrate what I just said. Here, first we can construct a 15-331 cyclic difference family. It contains 2 base blocks. We can check all the differences contributed by the 2 base blocks. The first one, 0, 1, 4, contribute the differences 1 minus 1, 3 minus 3, 4 minus 4. The second one, 0, 2, 8, contribute difference 2 minus 2, 8 minus 8, and 6 minus 6. So only 5 and minus 5 don't appear as the differences. So if we want to construct a cyclic design, we need an additional base block named 0, 5, 10, and then we can form all the base blocks we want to have and develop all these base blocks under the action of cyclic group of order 15, then can form a cyclic Steiner triple system of order 15. Okay, anyway, as a summary, I just want to see, if we want to construct a cyclic design without short orbits, we can we can try to construct a VK lambda cyclic difference family. If we want to construct a cyclic design with short orbit, we can use VKK lambda cyclic difference family. In the following, I give a short, brief introduction on the study of cyclic designs. Kirkman in 19th century showed that an Steiner triple system of order V exists if and only if V is 1, 3, modulo 6. He obtained these results by using 2 recursive constructions. One is just I wrote it here. He proved that if there is an STS-V, then there is an STS-2V plus 1. That means because we have known that STS-7 exists, so using this construction, we know STS-15 exists. And another recursive construction is V from V2 to V minus 1. Kirkman only used these 2 recursive constructions, and together with only one small example, that is the STS-7, then he can prove the necessary condition V is 1, 3 modulo 6 is also sufficient. And of course, at that time, even though Kirkman proved this problem, but many people don't know this problem had been solved. So Anstice in around 1852 to 1853, he still wants to solve this problem, but he used different approach. He wants to construct an STS-V with additional algebraic structure. Of course, the simplistic case is how about the existence of cyclic STS existence. So he constructed the first infinite families of cyclic Steiner triple system, and he used primitive roots. So maybe he's the first one to use the primitive roots to study design. Hafter in 1896 to 1897 first asked what's the existence of cyclic design, or using difference families language, he asked what's the existence of V31 cyclic difference family and V31 cyclic difference family. Just as I said, the former cyclic difference family used cyclic design without short orbits, and the later one used cyclic design with short orbits. And Hafter's difference problem was eventually solved by Pentelson in 1939. And his proof actually is a direct construction. In design, when we say direct construction, we mean she lists all of the base blocks explicitly. So it seems that a little mysterious when people first see she lists all of them explicitly. So 20 years later, after Pentelson's Golem gave an alternative approach, such that Pentelson proof seems understandable or seems more mathematics. So this solves the Hafter problem. Okay, we record the definition of CDF. We know the general parameter is V, H, K, 1. Here, the second parameter is H. So here, Pentelson solved the cases of H is 1 and 3. For the general case, H, the general case was solved by Wang Xiaomiao and Chang Yanxun in 2009 in direct constructions for most cases. This is story for K23. How about K24? Hanani showed that V41 design exists if and only if V is 1 for modulo tribe. The same, the technique is recursive constructions and direct constructions, but he don't solve the case for cyclic case. So the next question is, how about the existence of cyclic V41 design? First case people solved is when the V is a prime P. That means how about the existence of P41 cyclic difference family with P prime, and P is 1 modulo tribe. Both in 1939 first considered this problem. He provided a sufficient condition for the existence of a P41 CDF, but actually he considered a stronger condition to the cyclic difference family. He required his constructed CDF with a multiplier of order 3. And Brady in 1995 continued both the study. He showed that both CDFs, the existence, the necessary condition is also sufficient. And in the same year, Brady considered more general cases. More general means he just considered the existence of P41 CDF. He didn't require it admits an multiplier of order 3. And the tool he used is the Wheel theorem of multiplicative character sums. Use these tools, he can show that for sufficiently large prime P, and P is 1 more modulo tribe, then a P41 CDF always exists. And in 1999, because Michael Brody just mentioned when V is sufficiently large, so how about the lower cases of V? And for the lower cases, Chen Kejun and Zhu Lie, first they improved the bound of V, and then they use the computer search to solve all the smaller cases. So now people can see for any prime P is 1 modulo tribe, P41 CDF always exists. And so the next case is how about P441? But here, according to definition, P441 cannot exist. Actually, because the first parameter V must be a multiple of 4. So P441 does not have no meaning. So it must at least be 4 times P 441, or 4 times p to the n 441. And Checker and Coben first considered this case. And Brady constructed 4 times p 441 CDF for any prime p is 1 modulo 12. And actually, in 1997, he gave a recursive construction. I mean, in the second reference, just you see in this page, the approach Brady used is a direct construction. I mean, he lists all the base blocks. And actually, in 1997, Brady gave a recursive construction. It says if there is a pk1 CDF with a p prime, then there is a k times p kk1 CDF. So 1k equal to 4. A p41 CDF exists when p is a prime, just I showed in the last slide. Then 4 times p 441 CDF exists. So that means 4p 441 CDF's existence have two different proofs. One is direct constructions according to the second reference, and one is the recursive construction by the third reference. And anyway, there are many recursive constructions I will not mention in this lecture. I just mentioned several references. The most of the standard recursive constructions can be found in Coben and Coben's paper in 1984. Essentially, the tool they used named difference matrices. In my second talk on April 2, my main research topic is on the difference matrices. And Chang Yinxun and Miao Yin gave a concept of a new concept related on difference matrices named incomplete difference matrices. It's very useful tool to study difference family. So I list their paper as a second reference. And Brady's paper is also important because if you want to construct difference families over certain group, not just cyclic group, the third reference is very useful. Anyway, in Reid and Rosa's survey in 2010, as the first two open problems they asked, how to find a direct proof for the existence of V41 design, and whether the necessary condition for the existence of cyclic V41 design is also sufficient. And actually, the same question also asked by Coben and Mason in 1980. 2 years ago, one of my PhD, Zhao Menglong, and my colleague, Wang Xiaomiao, we together solved the existence of cyclic V41 design, or using the cyclic difference families language, we can solve the first case. 1H belongs to 1, 4. A GHH41 CDF exists if and only if this condition satisfied except for the three cases. Our approach is use direct construction. I will talk about it later. Okay, so when the existence of cyclic design solved, that means when the H is 1, 4, the existence of CDF we have solved. For the general case, the known results on the existence much smaller. Okay, I will mention two standard reference on this topic. 1H equal to 2, 2p241 CDF exists for any prime p is 1 more 3. And 1H23, 3p341 CDF exists for any prime p is 1 more 4. And this is the two classical results. 1H is not 1 and 4. Here is 1 and 2 and 1 and 3. And recently, Chang Yanxun and Chang Yanxun's master student, Shao Chenyan, and my PhD, Zhao Bingwei, and Wang Xiaomiao, and my PhD, Zhang Menglong, we solved the case of H belongs to 2, 3, and 6. So That means combining our last results, when h equal to 1, h equal to 2, 3, and 4, and 6, the existence has all been solved. The technique is still the direct construction. I will talk about it later. Okay, this is the story for the base block size 4. And how about base block size greater and equal to 5? The known rates are very small. Anyway, for the general base block size k, the most famous result is this case. It's from the finite geometry. We know that the points and lines of PGNQ forms a Steiner system, and actually it forms a cyclic Steiner system. And according to the even or odd of the value of n, it forms this parameter CDF or this parameter CDF. Okay. I will not omit the details of how to construct it. I list it here. If someone interested, you can see the slides later. Of course, we want to know if we want to construct other cyclic difference family, not with the parameter, for example, q plus 1. Here, q is a prime power. So how to do it? So one approach is to use cyclic classes. So in the following, first I will give some example on how to use cyclic classes to construct cyclic families. Okay, here let Q is 1 modulo E be prime power, and C0 E be the group of non-zero is powers of FQ. Let omega be the primitive element of the finite field of order Q, and the notation CIE are the cosets of C0E in FQ star, and called the cyclic classes of index E. Okay. Okay, here we see an example of how to use cyclic classes to construct a cyclic design. Here we want to construct a P41 CDF. Here P is 1 modulo 12 is a prime. So we can let P equal to 12 times T plus 1. We can count the number of base blocks. The number of base blocks is P minus 1 because there are P minus 1 non-zero elements. And each base block is of size 4, so it contributes 12 differences. So the number of base blocks is P minus 1 over 12 is T. So we need to construct T base blocks. And here we give an initial block, 0, 1, x squared. We call it an initial block. This initial block can produce T base blocks. Here, the variable I ranges from 1 to T. So one initial block produces T base block. Okay, we can check why it is a P41 cyclic disk family. We list all of these differences. Here, the pair 0, 1 contributes the elements 1. 0x contributes the difference x, 0 x squared, 1x, so x minus 1, 1x squared minus 1, x squared minus x. So this is all the differences. And in this example, we can notice that minus 1, we know it is equal to the omega to the p minus 1 over 2. P minus 1 over 2 is 60. So minus 1 equals to omega to the 60. So the set of these differences equal to the following. Here, after the dot, here is the C06. Okay. So if we want to, all of the differences cover the non-zero elements of the cyclic group of order P, we just require all these 6 elements belongs to 6 different representative system of the cosets of C06 in FP. Okay, and this can always be done using the following theorem. Okay. The following theorem actually is a corollary or is it's obtained by use the Will theorem. Okay. Anyway, first let us what the theorem said. Okay. First we look at this set. I colored it in blue. The capital X. In the capital X, we have some elements X, and we require each X satisfy X minus some element Bi belongs to a cyclotomic class. Okay, we want to know whether the set X is non-empty, or that also means whether there is an element X such that X minus Bi belongs to certain cyclotomic condition. And this theorem says when Q is sufficiently large and such capital X is not empty. So generally, we can use this theorem to give an upper bound. For example, in our last slide, we require all the these C numbers 1x, x squared minus 1x squared minus 1, x times x minus 1. They belong to different representative systems. So we can use the theorem to give a bound. P1P is greater than Q63 around this number. Then this CDF always exists. 1P is smaller than this number. We can construct it using computer directly. Okay. This theorem actually in literature, we generally quote the first paper and the second paper at the same time because they give this theorem independently, even though the first paper published in 2009 and the second published in 2004. Actually, in 2004, Brady wrote another paper on optical orthogonal code. In that paper, he mentioned the idea of this proof, but he didn't give a general case. But anyway, we generally quote this theorem at the same time using these two references. Here, I give another example. Maybe you will see why I give another example. Because I will use the example to introduce my next slide. Okay. In our last example, okay, we record. In our last example, we give P41 cyclic difference family. Okay. Here we give an example 3 times P 341 cyclic difference family. Here P is a prime 1 more 4, so P and 3 are co-prime. So if we want to construct a cyclic difference family of order 3P, Z3P, so Z3P is isomorphic to Z3 times CP, so we can construct this family over Z3 times CP, and it contains a whole. We generally in design we always call Z3 times 0 is whole. Okay, and first we can count what's the total number of base blocks. Here, the total number of differences is 3P. And because there are 3 elements cannot appear, so the admissible differences, the total number is 3P times 3. And each base block contains 12 differences. So 3P times 3 over 12 is P minus 1 over 4. So we need to construct P minus 1 over 4 base blocks. But here, I just only list one initial base block. This initial base block will form P minus 1 over 4 base block. You can see here C02, we know it's all the squares in the field. So it contains P minus 1 over 2, and this is a quotient group, so P minus 1 over 4. So 1 produces P minus 1 over 4. And then we can check all of its differences. For example, take the first two, 0, 1, 0, minus 1. It contributes differences 0, 2, or 0, minus 2. And note that here, P is 1 more 4, so -1 is a square. So the -1 can be absorbed by the quotient group to form the C0. Okay. Anyway, one can check all the differences are listed here. And here we want to all the non-zero elements except for the Z3 times 0 appears exactly 1 time. So for example, the first two differences is 0, 2 and 0, 2 times x. So because okay, we can omit 2. So the first one we can see 0, 1. The second one is 0x. So 1 is a square. So if x is a non-square, then all the non-zero elements with the first coordinate 0 appears. Okay. So anyway, this is a simple example. Okay. Why I give the example? Because generally, when we construct a cyclic design, first consider case is a prime case. So if the case is not a prime, how to do it? We know any number can be written as some product of primes. So for example, here 3 times p. And that means we can construct it on these 3 times zp. So that means we can first construct its first coordinate and then construct its second coordinate. And from this example, we can observe what's the behavior of its first coordinate. Its first coordinate consists of 4 elements, 0, 0, 1, 1. Actually, these 4 elements form a special difference family. We call it strong difference family. We can, okay, let us see what's the definition of strong difference family. The only difference of the concept of strong difference families and difference families is we require the dart flower F cover all of the elements of G, each element of G, the same times, mu times. I mean, 0 can be appear as a difference. This is only differences of this concept and our traditional concept. Take our example in the last slide, 0, 0, 5, 1, 1, these 4 elements. Okay, it forms a base block. We can check all of the differences contributed by the pairs. 0, 0 contribute 0 as a differences twice, the left 0 minus the right 0, the right 0 minus the left 0. And 1, 1 contributes 0 as a difference another 2 times. So 0 as a difference appears 4 times. Similarly, 1 or -1 appears as a difference also 4 times. So this forms a 3, 4, 4 strong difference family. Here, we use as means the strong to distinguish this concept and the traditional concept. So anyway, in this concept, we know that because 0 must occur as a differences, so the index mu must be even because the left element minus the right element and the right element minus left element. If it is 0, 0 must occur as a number. Okay, so let's return our last slide. Okay, that means first we need to construct a strong difference family. For this example, we need to construct a 3, 4, p minus 1 strong difference family. Here, p is 1 more 4, so p minus 1 is a multiple of 4. In this example, 0, 0, 1, 1, we have seen that it forms a Z3, 4, 4 strong difference family. So we take p minus 1 over 4 copies of this strong difference family. Of course, it forms a Z3 for p minus 1 strong difference family. Okay, we use it as the first coordinate of our example. Okay, a little summary, and I just want to see, we want to construct a difference family. And if the order is not a prime, it's a two product of some numbers. For example, we can construct a difference families over group G times a finite field FQ, and we can first, in its first coordinate, construct a GK Mills round difference family. Then, when the first coordinate arranged well, then we arrange its second coordinate according to some cyclotomic conditions. And finally, using the Will theorem or the theorem I just showed you, people can show that the second coordinate can always exist. And finally, to obtain the existence of a difference families you want to be. And anyway, this is here in this slide, I just list a possible approach. And actually, there are many other similar approach, but the basic idea is the same. The first construct a round difference family, and the second coordinate satisfy some condition. Okay. Anyway, we can use this simple idea to get many asymptotic results. For example, we can show there is an Fp times Fq, Fp times 0, P lambda difference family when P is 1, 5 modulo 12, and Q is sufficiently large. Anyway, this is a very useful tool to study difference families. So that's why I talk about it. Okay. And this result is an asymptotic result. Of course, we can also ask whether we can get some concrete examples. Yes, it can work. Just we need to take some specific strong difference families and take some specific number, for example, Q, E, N, D, and if it satisfies this condition, then we can get some concrete examples here. I list some concrete examples. We can get some two designs with block size 7, 8, or 9. All of these two designs are unknown before that in the handbook of combinatorial design theory. Why I'm interested in this number? Because on the existence of two design with block size 6, 7, 8, 9, in the literature, people have known when the size V is sufficiently large. Sufficient means not too big. Maybe V is greater than 1,000 or 2,000. I just mean only several examples are unknown. For the bigger V, the existence has been solved. So that's I'm interested in such kind of values. Okay. In the following, I will talk a little about the direct construction. Just I said, we can solve the case of existence of cyclic two design. First, I will give the definition of difference packing. Let H be a subgroup of group G. If as a differences, H dot flower F covers every element of G minus H at most lambda times, then we call it difference packing. If at most replaces as exactly, then the difference packing is a difference family. Okay. So the number of base blocks of cyclic difference packing is no more than this number. There are lambda times V minus H differences, and each base block contributes K times K minus 1 differences. So the number of base blocks is no more than this number. And if a cyclic difference packing achieve this number, then this cyclic difference packing is said to be maximum. In 1992, Yang Yixian and Lin Xuduan, in their book written by Chinese, they construct V41 cyclic difference packing. Here, V is 1 modulo 72. Actually, I believe they want to construct a cyclic difference family, because 1V is 1 modulo 72. It satisfies necessary condition of cyclic difference family with block set 4. And the number of base blocks of a cyclic difference family should be V minus 1 over 12. But they only can construct V minus 1 over 12 minus 3 base blocks. So they construct a packing, not a design. Okay. Okay, let us first review their construction. Let V equals to 7 times 2, 70 times 2, 72 times T plus 1. And first we count the number of base blocks, V minus 1 over 12. So V minus 1 over 12 here equal to 6 times T. So the number of base blocks is 6 times T. And all of the base blocks are divided into 6 parts. Each part consists of T base blocks. This is the desired case, but in their construction, here we can see this is their construction. All of the 6 times T blocks are divided into 6 parts. And for each part, there is a variable I. Here, T is fixed. 1V is fixed, we can see, because V is 72 times T plus 1, so T is a fixed number. So some number times T plus I is this number, and sometimes some number times T plus 2I plus some number, and some number times T plus 3I plus number. This is the format of each base block. And here, the capital I1, I3, and I6 consists of elements arranged from 1 to T minus 1, and I2, I4, and I5 consists of all the elements from 0 to T minus 1. So we know that if I1, I3, I6, if it's equals to I2, I4, I5, I mean, all the I comes from 0 to T minus 1, then we can have 6 times T base blocks. But here, if this one is 0, then when we check the difference, there will be some error appearing. So that's why they can only construct 6 times T minus 3 base blocks. Our approach is very simple. We just relax their condition. We require I1, I2, I3, I4, I5, I6, they all the same. Here, they use I range from 1 to T minus 2, and I cannot be the half T. Okay, so that means for each case, 3 base blocks are dropped, and there are 6 parts. So that means 6 times 3. The total base blocks dropped is 18. That means first we construct 6 times T minus 18 base blocks. And then for the remaining 18 base blocks, we can use computer to resemble all of the remaining differences to form our desired the remaining 18 base blocks. The idea is very simple, but it's very effective. And the next question is, here V is 72 times T plus 1. How about the other cases? For example, how about 72 times T plus 13? And so we need to observe why 72 plus 1 work. And this is a table. It lists all the differences contributed our base blocks. Okay, for example, here in this slide, the first two elements is 0, 43 times t plus I. So here it contributes a difference 43 times t plus I. So here at least 43t plus I. And these 6 numbers are the differences contributed by the first blocks. Okay, by the first blocks. And these 6 elements are the elements contributed by the 7, by the third base blocks, by the fourth, by the fifth, by the sixth. Okay, this is all the differences. And because here I ranges from interval, so here for we record that I range from 1 to t minus 2, and I cannot be this number. And so we can write the interval covered by the 43 times t plus I. Okay. And then finally, we can check all of the intervals are disjoint. Okay. So they form a difference packing. Okay. This is the case for 72 plus 1. And when we consider the 72 plus 13, we can see what's the problem will happen. Okay. First, in this page, we can see when the difference is 43 times t plus I, this number is bigger than the half of v. Half of v is 36t times I. So when the number changed from 72 plus 1 to 72 plus 13, and this difference will change. I mean, we need to use this number. And if the difference is lie in the former, it will not produce a problem. Okay. Anyway, I mean, when we change v to 72 plus 1 to 72 plus 13, okay, we can see the blue one here, this range, 28t plus 14, 29t plus 12, and this number, 29t plus 1 and 13t. These two intervals intersect. So there will be some problem appears. And how to overcome this problem? A simple idea is we just need to, okay, for example, this blue one is not good. So maybe we can use not 33 times t plus I. We can change it another, maybe 33 plus I plus 2 or plus 3. I mean, we can do a little change on this value. Okay. Okay, let us come back to our first model. That means we can only change the values AR2, BR2, and CR2. We can only change these 3 values to construct the case of V is 72 plus 13. And the same idea can be used to construct many other cases of V. Okay. Okay. This is the approach we solve the existence of cyclic design. And next, I will see a little application. And first, I will see the optical orthogonal code. And this code can be used in the OCDMA and first systematically investigated in 1989. And here I just want to give a simple definition for OOC. Okay, I will don't use the original definition. First, we record the notation of VDWQ code. VDWQ code here, Q means the Q array code, and each code word is a vector of length V. And here, D means Hamming distance, and W means each code word contains W non-zero elements or the Hamming weight. A VDWQ code is cyclic if take any one code word from the code and we can do a cyclic shift and it is also code. So this is the definition of cyclic code. VK1 OOC is nothing but a cyclic V 2 times K minus 1 K2 code. That means it is a 2-array code, binary code, 0, 1 code. And the Hamming distance is 2 times K minus 1. And the Hamming distance is 2 times K minus 1. Hamming weight is K. That means we can take the support of, from each code. And that means for any support of each code word, they intersect in at most one element. So that means VK1 also is nothing but VK1 cyclic difference packing. So they are totally equivalent. When the weight K is to 3, in the 1989 paper, they give a direct construction for the optimal V31 OOC. Optimal means the code attains the largest possible number of code words. So the next problem is how about the case of V41? Because we can solve the existence of cyclic design or cyclic difference family, so we can also we can use the similar tools to solve the existence of optimal V41 OOC. Okay, we can solve all of the cases. Actually, difference families can also produce maybe 3-array code, not only 2-array code. Lan Tao and Chang Lan Tao was the PhD of Chang in his PhD paper. He showed that a GHH41 cyclic difference family, here H is 1, 2, 3. Then there is the cyclic code. Here 6 means the Hamming distance and 4 means the Hamming weight. I will not show details of the relation of these concepts. I just want to say because we can solve the case of H is 1, 2, 3. So we have the existence of this code. Okay. And there is another interesting combinatorial coding named optical orthogonal signature pattern code. This code was introduced in 1994 or 1995 by Kitayama. Anyway, Kitayama in 2014 wrote a book. In his book, if you are interested, you can find some related topics on this code. And using our language, this code is nothing but cyclic difference packing defined on the 2 products of cyclic group. So, for example, when the order M and N are co-prime, the code OOSPC we shortly written is just an OOC. They are equivalent. When MN is a co-prime, they are equivalent. But for the general case, the existence of such kind of codes are still unknown. Anyway, this is still an open problem. And finally, I will talk a topic on difference families named disjoint difference families. A VK lambda cyclic difference family is disjoint and written as a JVK lambda DDF. When its base blocks are mutually disjoint. Here is an example. Okay. For example, if we take the 2 blue one, 2, 3, 6, and 1, 7, 9. Okay, we can see all the 6 elements are disjoint, and we can check all the differences. It can form difference families. So these 2 base blocks can form disjoint difference families of order 13. In 1974, Novak presented a conjecture. It says every cyclic Steiner triple system of order V is 1 more 6, can be generated V41 DDF. We still use the example to illustrate this conjecture. Okay, but in this example, all of the blocks are divided into 2 orbits. We can take one orbit 014 from the first orbit and another base block 027 from the second orbit. These 2 blocks form a difference family, but it's not a disjoint difference family. But if we take the 2 blue one, it can form a disjoint family. Novak conjectured that given any cyclic Steiner triple system, this Steiner triple system can always imply a disjoint difference family. I can show that this conjecture is true when the order V is a prime, just simply using the following interesting theorem given by Karasov and Petrov in 2012. Okay. Let F be an arbitrary field, and let M, D be positive integers. Let X1, X2, Xm, T1, T2, Tm be subsets of F, satisfying the following 2 conditions. And then there exists a system of representatives Ti belongs to capital Ti, such that the sets are pairwise disjoint. Maybe you don't know what I think, and what's the relation between this theorem and our problem. To apply our problem, we can think each xi be a base each xi be a base block. Okay, for example, in our slides, we can think x1 is 014, x2 is 027. These 2 sets intersect. So we want to give a translation of these 2 sets. So x1 plus 2 is this blue one, and x2 plus some number is this blue one. So the translation is the T1, T2, Tm. It is a number. So the result is the capital X1 plus T1, capital X2 plus T2, the capital Xm plus Tm are pairwise disjoint. So it can form a disjoint family. So this theorem said if these 2 conditions are satisfied, then we can always find a disjoint difference family. Okay. Still consider our problem. In our problem, the number of base blocks is p minus 1 over 3. Okay. P minus 1. The total number of non-zero elements is p minus 1. 3 means because we only consider the base block size 3. So each base block size can contribute 6 elements. So the number of base blocks is p minus 1 over 6. So we can take x1, x2, xm be our base blocks. And then we look at the first condition, xi minus xj. The size is no more than 2 times d. We can take d equal to 5. Because here, the size of each xi is 3. So this number is no more than 9. Anyway, we can take d to 5, then such that the first condition is satisfied. And the second condition, ti, the size of ti is the number of the for our example, we can take ti is all the elements of the cyclic group of 13, because the Ti can be 0, can be 1, can be 2, can be 3, can be 12. So it has the 13 elements. So here, the set of Ti is P, because we constructed this design in the cyclic group of order P. So the set of Ti is P, and M is P over 6. Okay, and 8 times D is 5. So P, of course, is greater than 5 times P over 6. So this theorem works. So actually, we can prove every pk1 CDF, here k is not must equal to 3 for any k work. Every pk1 CDF can use a JPK1 disjoint difference family. So anyway, the Kirchhoff and Petrov theorem is very interesting. It uses an unexpectable result. Anyway, I can give a quick look to his to their proof. Their proof will use Alon's combinatorial Nullstellensatz. The proof is very short. First, we can take small xi in capital Xi, small xj in capital Xj. We hope find the translation T1, T2, Tm such that after the translation, they are pairwise disjoint. So we hope xi plus ti is not equal to xj plus tj. And that means xi minus xj is not equal to tj minus ti. We know that here xi, xj are all coming from the base blocks xi. They are given. Okay, so this number is a fixed number. And we just want to know whether we can find the possible translation Ti, Tj, such that this inequality holds. So we can construct a polynomial. And first we set capital Xij is xi minus xj. And we observe this polynomial. Each term is of the form Ti minus Tj minus x. And x is in the capital Xij. And we hope find some Ti, Tj such that this polynomial attains a non-zero value, then the proof is complete. And this can be achieved by using Alon's combinatorial Nullstellensatz. I will omit the details. Okay, it's not difficult work to do it. Okay. Anyway, because we have an unexpected result, so we can make a general conjecture that Novak made in 1974. We can ask whether this conjecture holds. For any cyclic VK1 design, whether it is always possible to choose one block from each block orbit so that the chosen blocks are pairwise disjoint. And this conjecture can be made more generally. One can replace general index lambda. But in this case, we require the conjectures hold for bigger V. I mean, because we can always find some counterexamples when lambda is big. For example, we can take two cyclic symmetric design. For example, we can take cyclic STS7. We know it's a final plane. Any two lines must intersect. We can take two copies of final plane. And anyway, for any two lines, they still intersect. So anyway, it cannot form a disjoint difference family. Disjoint is possible. But the problem is only because of V is too small. The final plane contains 7 blocks. So when V is big, we conject it should be always okay. And we can give the following theorem to show the conjectures hold in many cases. Let k greater than or equal to 2 lambda plus 1, and let S is k minus 1 over lambda. And the conclusion is for each real number epsilon greater than 0, there is an integer v0 such that for each integer v is sufficiently large, any cyclic vk lambda design has a partial parallel class. A partial parallel class is a set of pairwise disjoint blocks such that this partial parallel class contains S-1 blocks from each of this number of orbits and contains S blocks from each other orbit. Okay, for example, when k equal to 3 and lambda equal to 1, the number S is 3 minus 1, that's 2. 2 over 1 is 2, so S equal to 2. So this result means any cyclic V31 design, we can any cyclic V31 design has a partial parallel class for almost all its blocks contains 2 blocks, and a little block orbits only contain 1 block, such that they are pairwise disjoint. Okay. Here I give a quick view of the proof or the idea of how we construct it. Okay, here I draw a picture. First, we have a cyclic design. So all of its blocks can be partitioned into some orbits. So this is a base. This is a block orbit. This is a block orbit. This is a block orbit. So here it consists of m base block orbits. The goal is to find some disjoint base blocks from each base block orbit. According to our statement of our theorem, we hope to find S disjoint base blocks from each base block orbit. I mean, we hope to find S disjoint base block orbits from the first base block orbits, the second S, the third S, the 5S, and almost S, only a little base block orbits, S-1. This is our goal, okay. We can form a uniform hypergraphs. How to do it? First, for each base block orbits, we add S new points. And for the first block orbits, for example, we add U11, U12, U1S. These are S new elements. And we join each element to the base block to form a k+1 set. We let it k+1 edge in a k+1 uniform hypergraphs. So we make a k+1 uniform hypergraphs. And then we can give edge coloring of the hypergraphs. So we know that, for example, we give edge coloring, and then we can take a color set. And we know in the color set, every 2 edges must disjoint. So in the first block orbit, for example, if we take the first line, and then we know because each line have the U11. So if we take the first line as an edge, we cannot take any other edge containing the U11. Anyway, we can do the edge coloring first. This can be always done by using the Hypergraphs and Steiner theorem on edge colorings of R-uniform hypergraphs. The theorem said every almost regular R-uniform hypergraph G. For our hypergraph, it is almost regular because we can count the small degree, small delta G is V minus K, and biggest degree is no more than V. When V is sufficiently large, K is a fixed number, so it is almost regular. And according to the theorem, it requires the hypergraph with small maximum codegree. And for our graph, the codegree is no more than K plus lambda plus minus 1. K and lambda are fixed small numbers, so compared to the value of V, it is very small. So it satisfies the condition of this theorem. According to this theorem, our graph can be edge colored with close to delta G colors. And so we can take a largest color class of our coloring. And we know when we take the largest class, for example, we back the picture, okay. For example, the color class contains S edges in the first orbit. Then we take this orbit. Maybe our largest color class can only contains S minus 2 or S minus 3 edges. In this case, we drop this base block orbit. Anyway, I mean, we can only take this one. The flower C restricts on M, gives rise to the required partial parallel class P. I mean, first, this is the first step. After the first step, we can construct a picture like this. In the left part, the size of the left part is big OV. And in each base block, there are S disjoint blocks. And in the left part, we take nothing base blocks. And the number of the left part is small v. And we can show that we have many good enough blocks. We can give the definition of good. Anyway, I mean, okay, for example, in the first orbit, we can take the first base block such that it can add it into the flower P. But when it's added in flower P, maybe in the right picture, the first orbit, in the first orbit, there will be some base blocks intersected with. But the property of P good can guarantee only one base blocks intersect with this one. So that means we can only destroy a small OV number of base block orbits such that it contains only S-1 disjoint base blocks. And finally, we give the proof, okay. Finally, okay. I mentioned a stronger conjecture by Novak. Actually, in Novak's paper, his conjecture is stronger than I just show you in our slide. He said, every cyclic STSV with V is 1 modulo 6 is generated by a symmetric V31 DDF. What's symmetric? Symmetric means, take this example. For example, this 2 green one, 2, 3, 6, and 1, 7, 9. These two are disjoint, but the number 6, when we see it's negative, negative 6 is 7. So the minus 6 equal to 7. So it's not good. But if we change another 2 base blocks, the blue one, the red one, 7, 8, 11, and 4, 10, 5, they are disjoint. and the -7, -8, -11, -4, -10, -12 also disjoint each other. So Novak make a stronger conjecture. He conjectured that every cyclic standard triple system can be generated by such a stronger disjoint difference families. So far, I don't know how to solve it, but small examples shows that we believe the conjecture should be true. Okay. This is my lecture today. Thank you.
Thank you so much for the lecture. Are there any questions to Tao?
Yeah. Well, I'd like
Oh,
to
yeah,
ask
please.
questions.
Yeah, sure. Akihiro, yeah, sure.
Yeah, so it seems the Novak is interested in a question whether you can choose disjoint base blocks, right?
Yeah.
In a difference family. But there's obvious upper bound on the number of disjoint sets that's roughly V over K.
Okay, sorry.
Yeah, K is the size of the block and V is the number of points. So you can't have more than V over K disjoint blocks.
Okay, you mean generalize this conjecture to general K?
No. I wonder whether this it is something to do with the obvious upper bound of the number of disjoint base blocks. Yeah, for example, if the number of orbits, it's so many that if the number of orbits exceeds V over K, then obviously you cannot choose disjoint base blocks. Does such a case occur, or it never occurs?
Sorry, I'm not very clear your question. Sorry, I'm not very clear your question.
Okay, so in a difference family, you have several base blocks.
Yes.
Does it happen that the number of base blocks exceeds V over K?
The number of base blocks is V minus 1 over K times K minus 1. Yeah. V minus 1 over K times K minus 1. So it cannot exceed.
I see.
V over K, yeah.
Yeah. Okay, so well, I see. So this is way smaller than V over K. So you can expect.
Yeah.
Okay, thanks. Yeah, I have two more questions. Can you go to page 22?
Okay. Yeah.
Yeah, I don't. So this conclusion of this lemma is written at the bottom. So it's about the existence of this difference family.
Yeah.
Which depends on the group G, which appear in the first line of the assumption, and also depends on the field FQ and also the integers K and lambda.
Yeah.
Yeah, but the assumptions are not clear. What are you assuming? First, are you assuming that there is a GK mu SDF?
Yeah. And then assume that the second coordinates must satisfy this cyclotomic condition. This means
okay. So the right
for each H belongs to G. That means given an element in the first coordinate, then we observe how about its second coordinate. We require its second coordinate satisfy this formula. Yeah.
I see. So there are two equality signs, but the left one is just a notation, and the right one is the real condition that it is the product of C0E and DH. Okay.
Mm-hmm.
I see. So this is a non-trivial condition.
Yeah, it's not
okay.
Non-trivial condition. Yeah.
Yeah. Okay. Thanks. And there's I have also a question on page 18 about the Bayes theorem. Can you go to 18? Yeah, I think this is just a minor thing, but
okay.
Yeah. So at the end, you have a bound small q is greater than capital QEM.
Yeah, capital QEM is this number.
Uh-huh.
Here
yeah, but
is the number.
But the way it is written, it is not clear whether this is a assumption or consequence. I suppose this is an assumption. The small q is necessarily greater than equal to capital QEM, and that was the hypothesis, is it?
Okay, it means okay, first the small bi, b0, b1, b minus 1 is some elements of FQ. So this is the requirement we want to achieve.
I understand. The conclusion you want to make is that this some certain set is non-empty. Yeah, I understand that part. But the for that to be true, I think you need to assume that small q is sufficiently large.
Yes, q is sufficiently large.
Yes. Yeah. So, but okay. So this very last inequality is a hypothesis, not the conclusion.
Yeah.
Yes.
Mm-hmm. Yeah.
Yeah, I look at the Bratti's paper, and then Bratti writes as soon as instead of and. But as soon as it is not clear whether the assumption or conclusion, but apparently, of course, as soon as that means they say essentially same as if, so it is the hypothesis. Okay. Yeah, that's all the question I have. Thanks very much.
No, thanks so much.
Any other questions to Tao? Well, actually, I have one very simple question about theorem by Karasev and Petrov. So it is slide number 36. So my question is about, are there any other applications you use where you use this theorem? So you use it to prove generalization. I mean, right here, in some sense, to generalize Novak's conjecture. But are there any other applications of this theorem?
You mean, are there any other applications of this in design or similar?
No, theorem by Karasev and Petrov. It is slide number 36.
This one?
Yeah, I mean this one, yeah. So you use this theorem by Karasov and Petrov to prove your theorem, right? Yeah, which was published on 2020 first. But my question is, are there any other applications of this theorem you can use in your theorem?
No.
No.
Yeah.
So it is the only application, right? Yeah. So
Yeah.
it gives, as far as I understood, it gives a set of pairwise disjoint families, right? Yeah, that is exactly what you need.
Yeah.
Yeah.
Actually, I don't know what's their original idea to give this theorem. Actually, you know, I have many students. So one day, one undergraduate students want to read some papers. So she asked me what topic can I give. So I said, maybe you can read something on combinatorial nullstellensatz.
Yeah.
So I just searched some paper, no purpose.
Yeah.
And she report the paper. I know, I just know this theorem. So I know it's useful for my question. So it's beyond my imagination. Yeah.
Interesting. Yeah. We need to ask Fyodor Petrov. He is from St. Petersburg. So we need to ask him what was the main idea.
Yeah.
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 I don't know.
Yeah, but of course, a set of disjoint sets are commonly used. So it is reasonable to consider. Yeah, interesting, very interesting. So you said for the strong Novak's conjecture, you believe that it is true, right?
Yes, yes. For all small values, it's true. Yeah. But it's too difficult because it contains almost elements.
Well, but did you make some computational experiments to check it?
Yes, yes. Yeah.
I see. I see. Okay, thank you so much. Any other questions? Okay, if not, then let us thank again Tao for this very interesting lecture. And actually, you give a very nice historical background about this problem and about different families and codes. So it was very interesting and useful. Okay, next lecture will be in 2 weeks on April the 2nd. And the title of the lecture will be as difference matrices and orthogonal automorphism of groups, right here?
Yeah.
Yeah, okay, good. Thank you so much. Thank you.
Thank you.
See you in 2 weeks.